maybe that's a commentary on my French. Thank you for the invitation. So I'm not going to talk about paleoceanography today, because I thought there wouldn't be many people who are interested in paleoceanography. So I'm going to spend the first half of the talk talking about the early Earth. And I should add, the early Earth is a hobby for me. So there are people in the audience who are really specialists of the early Earth. If I say anything that's not quite right, then be kind with me, correct me. But I'd like to show you some of the stuff we've done on the early Earth. I was also asked to start avec les éléments de base, start really with the basics. And so what I thought I'd start with is how do we get a solar system? And you'll kind of figure out why I'm showing this in a moment. So before we had a solar system, it's thought that in this region, in the region of space that we're in now, that there was a large cloud of dust and gas, and that it might have looked something like the Magellanic Cloud. And that was held apart by electrostatic forces. And something caused that cloud to collapse. And we've got reasonable reason to believe that maybe it was a supernova. So it was a gravitational collapse, the kind of final stages of a large star. And that's not a guess, it's because there are elements in early solar system, in meteorites, in planets. There are elements that are very short-lived, they're very short-lived, and some of those elements are heavy. They're heavier than iron, so they can have only been produced in a supernova. So we've got reasonable reason to believe there was a supernova that caused this cloud to collapse. Whatever caused it to collapse, it did. Oh, wrong way. So that cloud collapsed. As it collapsed, a disk was produced. That disk started to spin due to conservation of momentum. So it's kind of Newton's second law. As it collapsed, there was kind of gravitational heating at the center of that disk, and that heating formed our sun. And then in the outer parts of the disk, we had kind of dust and gas and kind of small particles of material. And those small particles of material, they started to coalesce, forming larger and larger bodies. And once those bodies got to kind of kilometer size, gravity took over, and those bodies started to attract anything that was in their vicinity. And that's how we think that, or it's our best idea of how the solar system was formed. So we're on one of those larger bodies that was produced by the secretion of material. Now the reason I mention this is the so-called nebula hypothesis, the nebula model for the formation of the solar system. So if this is correct, it means that the sun and the planets, they should have more or less the same composition. They were all produced from more or less the same material. And to an approximation, that's correct. So if we look at something like, this is an example of a very primitive meteorite. So this is amongst the first solid material that condensed in the solar system. And these calcium aluminium inclusions are thought to be the earliest thing that condensed in the solar system. If we compare the chemistry of these chondrites, these primitive meteorites, with the composition of the solar photosphere, you can see on this graph that it's more or less the same. So then the assumption has been that the Earth is more or less the same. And to a very broad approximation, that's correct. There are, of course, differences in the solar system. So the terrestrial planets are very different to the Jovian planets, and that's because these volatile elements, they weren't able to condense close to the sun. They could only condense kind of beyond the so-called snow line, where temperatures were cool enough that these volatile elements could condense. It's also kind of become apparent over the past 20 years from isotopes, from kind of subtle variations in different isotope systems, that there are differences in the solar system. So the planets, the terrestrial planets, we don't know anything about the Jovian planets, but the terrestrial planets, they have subtle differences that say that they're not exactly the same as the chondritic meteorites. But to an approximation, elementally at least, the Earth is thought to have been broadly chondritic. So what's shown here is a figure, condensation temperature on the horizontal axis, against normalized abundance. So that's the abundance of those elements in the silicate earth, the bulk silicate earth, so it's the mantle, continental crust, relative to chondritic meteorites. And you can see on that figure that the refractory elements, they're kind of more or less chondritic. Volatile elements have been depleted, so that might be because they never condensed, or it might be that we lost them early in Earth's history when the Earth was still very hot. You can also see that these so-called hydrophile elements, these iron-loving elements, they've been removed from the silicate Earth. And that removal is due to core formation on Earth. So we end up with a bunch of different terrestrial planets, and some of the larger planetesimals in the asteroid belt. They've all got metallic cores, they've all got silicate mantles, and many of them, or most of them in fact, they've all got crusts. They've got silicate crusts. So for a geochemist, those mantles, they potentially preserve information on core formation, they preserve information on formation of the crust on those different planets, and for the Earth at least, they provide us, that mantle preserves information on the recycling of crust back into the mantle. So that's kind of the premise that a lot of isotope geochemistry that uses. These bodies, they started off as chondritic, you made them core, you made a crust, and on Earth you started recycling that crust. But as I mentioned, there are a number of isotope systems that show that the Earth wasn't perfectly chondritic. There are some differences. So the biggest single differentiation event on Earth is formation of the Earth's metallic core. It comprises about 30% of the mass of the Earth. We've got an outer core that's liquid, an inner core that's solid, consists of iron and nickel, and a bunch of other light elements that change depending on the latest experiments or geochemical evidence that we have. For a geochemist, we can't look at the core. We've got no access to the core. But we know what the crust, we know the composition of the crust, and we've got a reasonable idea for some parts of the mantle. And so the approach that's often taken is that we assume that the Earth started off as chondritic. We know what's in the bulk silicate Earth, so anything that's missing, it must be in the core. If its behaviour suggests that it's hydrophile, that it would go in, that it would behave with an iron-like affinity. So that's the premise that we often use. So to study the core, we use the hydrophile elements. This is another one of these figures, abundance normalized to chondritic abundance, and on the horizontal axis, increasing hydrophile behaviour. So we go from elements like manganese and gallium, which are slightly hydrophile, nickel, cobalt, tungsten, which are moderately hydrophile, and then platinum group elements, rhenium, gold, which are highly hydrophile. Now these moderately hydrophile elements, they've given us a huge amount of information on core formation and on the conditions of core formation. And I'm not going to go into that in too much detail, but I'll give you just show you a couple of examples. So it was realised quite early. So this is log of the partition coefficient against pressure in GPa, and these are experimental curves showing the partition coefficient between metal and silicate as a function of pressure. Now, composition of the mantle is here, it's kind of on this grey line here. And it was realised some time ago, maybe 15, 20 years ago, maybe even more, that equilibration in the Earth's mantle between metal and silicate can't have occurred at low pressures. It must have occurred at high pressures. And this is a compilation of a number of experiments. I think maybe there's even one of Ali's experiments in here, I'm not sure. No? Oh, I'm sorry. But Ali has calibrated these curves a number of times. They're probably the best, but this was the one I found. But the important thing that they show is that metal-silicate equilibration appears to have occurred at great depths, between 30 and 50 GPa, which corresponds to depths of between 800 and 1200 kilometres. And experiments like this have been taken to suggest that this equilibration occurred deep. So why did it occur deep? Well, it's taken to support the notion that the Earth, the early Earth, the outer part of the early Earth was entirely molten. It was covered with a magma ocean. And those pressures that we see from those metal silicate equilibration experiments, they correspond to the final equilibration between metal and silicate at the base of that magma ocean. Those aren't the only experiments, but I just wanted to show you briefly those experiments, to show you the type of work that's been done, and that's being done here. Is it being done here? Maybe not, but there's the possibility for it to be done here if anyone wanted to do it. The other thing you can do with these modularly hydrophile elements is you can get some kind of age estimate from the core. What you need to date the core is you need a parent-daughter system that's fractionated during core formation. And hafnium tungsten is kind of ideal for that. 182 hafnium decays to 182 tungsten. Tungsten is hydrophile, so it will go with the metal into the core. Hafnium's lithophile, so it'll be retained in the silicate mantle. This is a very short-lived isotope. 182 is a short-lived isotope. It has a half-life of about 9 million years, which means it's pretty much all gone after about 60 million years. So we can only use this to date the core if core formation occurred within the first 60 million years of the solar system history. So next figure is just to show you how that works. Keep blinding myself if I walk over here. So we know we can walk over here all the same. So if we assume that the Earth started off as something broadly chondritic, we can measure the phases in those chondrites to get an initial ratio. So we can get an initial tungsten isotope composition from chondrites. We can measure them at the present day, the bulk, to see where they've evolved to. So if you made a planet and it didn't differentiate, it remained kind of primitive material that didn't melt, and it was chondritic in composition, then it would follow this curve. However, if you make a core, sometime while 182 hafnium is still alive, then all the tungsten will go into the core, very little hafnium will go into that core, so you'll have a core with a low parent-daughter ratio, which will evolve to a relatively unradiogenic composition. And what will happen if you make that core, you'll leave a mantle that's got not much tungsten in it, but a lot of hafnium, and so the composition of that mantle will then evolve to a radiogenic composition. So if we can measure the tungsten isotope composition of the mantle or any crustal rocks of a terrestrial planet, and we know the parent-daughter ratio, then we can calculate back, it's a simple calculation, to when that mantle had the same composition as chondrites. And that's taken as the time at which core formation occurred. So this is some early data for the Earth. I think this dates 2003. I can't remember whose paper I stole it from. But what you can see is that silicate Earth is quite different. It's much more radiogenic than chondritic composition. And you get, if you calculate single-stage model back to what it should look like when it's chondritic, you get an age of 30 million years. So at the time that this data was published, that was taken to be a kind of mean age for the formation of the Earth's core. People have subsequently realized that the Earth is much more complicated than that. We didn't just make the Earth in one go. We accreted it. It grew over about 100 million years. Some of that growth involved very large collisions, like the lunar forming impact. And we can't be absolutely certain that what we measure in the mantle today hasn't been perturbed by some of those impacts. So we may have had impacts where core material in the impacting body went straight to the core. We may have had impacts where that core material mixed with the Earth's mantle. Also, over recent years, it's become apparent that the Earth's mantle today isn't entirely homogeneous, it's heterogeneous. But this kind of shows in principle what you can do with those systems in terms of dating the time of core formation. Okay, so what I'd like to talk about for the rest of the first part of the talk is these highly hydrophile elements. They're kind of paradoxical. So they're depleted, and they're depleted more than the moderately hydrophile elements, but they should be much, much more depleted. Low pressure experimental data suggests that they should be abundant in the Earth silicate mantle. They should be kind of down here somewhere. And that's shown a bit better on this present figure. So that's kind of what we see in the Earth's mantle. 2 orders of magnitude less than chondritic abundances. Whereas these low pressure partitioning, metal silicate partitioning experiments give you kind of down to 10 to the minus 15 for platinum. So they're much more enriched than they should be, but they're also present in chondritic proportions. It's a flat line. We don't see the variability that you'd expect from this low pressure partitioning data. So this is an old problem. We've known about it for a long time. We've known about it more or less since we were able to measure platinum group elements with any kind of precision. And there are a number of solutions to that problem, which I go through now. So kind of the most popular solution is a so-called late veneer model. And that late veneer model is really explained by the addition of, there was the late addition of meteoritic material to the Earth after core formation had ceased, but before the magma ocean had completely solidified. So that's the late veneer model. Another model, which kind of became popular 15 to 20 years ago, when experimentalists realized that at higher pressures, these highly hydrophile elements.
Just one quick, why you add this before solidification of the mantle? Late veneer.
Because you need to be able to mix that material in. So the notion is, now I'm not saying it's correct or not, but the idea is that you add it while the magma ocean's still liquid, and then it can be mixed into the mantle. Otherwise, if that had cooled, it would be much harder to mix that material in. It would be effectively resting on the surface of the Earth. Now, it's kind of a conceptual thing rather than... but that's the idea, that's why. It's not me that made that up.
No, just
I wish I had.
Just
yeah, so that's the idea. Somehow you need to mix that material effectively into the mantle.
You mix the mantle 4 times, something like that, no?
On the Earth, yeah, but maybe not on some other planets. But we'll get to that in a moment. Is that okay? Yeah. So highly hydrophile elements, they become less hydrophile at high pressure. So maybe at the base of a magma ocean, they become less hydrophile. Well, they do become less hydrophile, but maybe that can explain the abundances that we see in the mantle. Another model, which people never talk about, or very rarely mention, is inefficient core formation. So in this model, you can imagine that in a magma ocean it's easy to separate metal and silicate. It falls down as droplets, they're both liquid. So you can separate silicate from metal very easily there. Now if the Earth had a magma ocean that went all the way to the core, then separation would be relatively simple. But most modelling suggests that even if it was once molten all the way to the core, that situation only prevailed for a few tens of thousands of years. So at some point, it's likely that that metal had to migrate through a solid crystalline framework. And in that case, it's almost impossible to completely extract the metal from the solid crystalline framework. So it's often ignored because people don't like it, because it doesn't kind of fit in with the kind of exciting possibility that the Earth received a late veneer. But it's really difficult to rule that model out.
It's also difficult to constrain it.
It is, yeah. But you can say from the experimental work that's been done, it's almost impossible to extract a metal from a silicate framework 100%.
If it's a solid, no.
Yeah. So,
silicate is solid.
Yeah.
But with this model of inefficient core formation,
yeah,
you must expect not to having the flat of highly hydrophile elements, because the partition coefficient of elements are different. So if it is true that is...
But they would be highly concentrated in that metal. But
no, what I'm saying,
yeah,
the pattern of the highest of elements in the metal should not be flat.
Shouldn't be flat.
Yeah.
Okay.
If the inefficient core formation is the predominant or the dominant mechanism?
I think the calculations we've done, it's not very different. But yeah, I haven't got those here, so.
We can discuss this later. But
Yeah, I mean this is a mean as well. It's probably more like a, you know, there's a bar of uncertainty there.
So, geodynamic sense, you are saying that compaction is incomplete.
Yes.
Okay.
Yeah. And that it's very difficult to make it complete.
Okay.
I don't know if that's the case.
It just depends on the D, right? The more extreme the D is, the
Yeah.
closer to flat.
Yes,
So it's
yeah.
the moderately solidified elements tend to give you that deep range.
Yeah. But that. Yeah. Okay, so high pressure equilibration. Experiments, this is the result of experiments, so you can see that for platinum, palladium, rhenium, it kind of works, although not in every case. Some experiments suggest it works, sometimes it doesn't. But for osmium and iridium, it doesn't. And so it's kind of more or less assumed after 15 years of these kinds of experiments that high pressure equilibration can't account for the abundance that we see in the Earth's mantle. Now, we might find that there's some other control that means it does, but for the moment it doesn't look like there's some kind of unique pressure at which all the HSEs are partitioned more or less the same. And so people have kind of gone back to the late veneer. This was the first model. There's a problem with the late veneer, and that's kind of illustrated in this figure. So this is the abundance for Mars, red, green is the Earth, and there's the Moon. So you'd expect if the Earth experienced some kind of late addition, late veneer, that the amount of material that it received is more or less the same as the Moon. It's got a different cross-section, but they're both sitting in the same area of the solar system. So you'd expect them to experience the same amount of late addition, but as you can see from that figure, the Moon has kind of 2 orders of magnitude less highly hydrophile elements than the Earth. So that was often seen as a problem. One possible solution that was put forward by a planetary dynamicist, and again I've forgotten to put his name, sorry, I think it was Botkin who did this modelling. So he figured out that by the time the Moon was formed, most of the projectiles left in the solar system, they'd be large. They'd be 100 kilometres or larger. And so what he suggested was that it wasn't constant addition of fine, and you can see there's a trade-off here between diameter of the projectile and number of projectiles to give you the concentrations that we see on the Moon, Earth and Mars. And he suggested that by the time the Moon, well, by the time in particular the Earth stopped accreting.
I have a question on that. Sorry. The difference between the Earth's mantle and the Moon rules out the third solution where the iron should be retained in the mantle, does it?
It does, except you've got different. So the Moon was formed under different circumstances. So yeah, but yeah.
Or maybe the core of the Moon would be that extra metal that would settle down afterwards. That's the second possibility.
Yeah, I mean the core of the Moon is quite small, if I remember correctly.
But you don't need.
Yeah.
Maybe something I don't know how the measure the composition of the Moon is the sampling of the.
So we can do it from. I mean, we're lucky with the Moon. We have lunar meteorites.
Meteorites.
Yeah, lunar meteorites or samples brought back by the Apollo missions.
Okay, because all the direct sampling we have is on the visible side of the Moon.
Oh yeah,
maybe
so
there is a bias.
yeah, maybe there is a bias, but it's true. Maybe there's a bias. We never know, and that's the same for any kind of meteorites that we work on or lunar samples. There might be a bias, but this data comes from both lunar meteorites and Apollo samples, and it's also from crustal rocks. And there are some inferences that we have to make to work out the composition of the mantle from a crustal rock, and I'll show you those in a little while. Anyway, what the idea that Botkin came up with was that it wasn't this constant rain on the Earth and on the Moon, and that well, here's some of his other modelling. It's this so-called stochastic late accretion, and he showed that after 10 million years, most of the bodies left in the solar system would be big. They'd be 100 kilometres or more, and so you only have to add a few more to the Earth than to the Moon, and you can make up that difference. I don't know whether that's true or not, but that was the way round that people found for this so-called late addition. So in terms of melt, in terms of...
Basically what you're saying is the one got lucky and the other one not
Exactly,
lucky.
yeah. One was big and was able to receive big bodies. The other, if it had been hit by one of them, you know, who knows what would have happened. I certainly don't. Okay, migration, metal migration, or any melt migration through a solid framework is determined by the solid-solid interfacial energy relative to the solid-liquid interfacial energy. And that's manifest as this so-called dihedral angle. Now, if that dihedral angle, so that's the angle, if any melt is trapped at a grain corner, if that angle is less than 60 degrees, then the melt can be interconnected. If it's greater than 60 degrees, then the melt gets trapped along varying boundaries, and it can't migrate through. So for a long time, it was thought that the metal couldn't migrate through a solid framework. And so there were models in which metal moved from the base of the magma ocean to the core as large diapirs, like a granite. Then there was some experimental work that was published in 2013, where they found that there was a pressure dependence on the dihedral angle, and that once you got to pressures of 50 GPa, it's not shown so clearly here, but once you get to pressures of 50 GPa, the dihedral angle for metal and silicate, it shifted to less than 60 degrees. So percolation's possible through a solid framework, crystalline framework, but we still don't know really how much of that metal you can remove from the base of the mantle. So that's kind of the inefficient core formation model. Okay, so why do we care? Why do we care about the late veneer? Who cares? 0.5% added late during our secretion. Well, one of the reasons we care is that a lot of people think that maybe the late veneer brought the Earth's water. If the Earth accreted dry, then we have to have some mechanism to bring the water to the Earth. So maybe it's the source of the Earth's water. It's just a simple calculation. So if the late veneer was entirely carbonaceous chondrite, which is extremely unlikely, but I've taken that, it's kind of just a way of just to show you those calculations. Carbonaceous chondrites contain about 15% water or more. So if we added 0.5% of the mass of the Earth in this late veneer, and it was carbonaceous chondrites, then there's enough water there for 3.2 oceans, or just over 3 oceans. So they could bring. Now, ordinary chondrites, enstatite chondrites, they have a lot less water. Just to make a comparison though, if the Earth accreted wet, and it was entirely carbonaceous chondrite, there's enough water for 400 oceans. So people often give this as a reason as to why the late veneer is important. I guess it's also important from a more fundamental basis, trying to understand how the planets formed, how they accreted. But it's very difficult to know whether the Earth accreted wet, and we lost some of the water, and we've got just about enough left for an ocean on the surface and an ocean or two in the Earth's interior, or whether we did get all the water from the late veneer. Okay, so now I'm going to finally show you some work that we did. So a few years ago, we made some measurements of highly hydrophile elements in other planetesimals and planets. One of those sets of measurements was from a suite of meteorites that are thought to come from Vesta. Vesta is the second largest body in the asteroid belt. It's about 500 kilometers across, 500 kilometers diameter. For Vesta, it's thought that core formation is relatively rapid. Tungsten hafnium age is less than 4 million years. So it means you've got a short time for core formation, and you've got a shorter time. It's also thought that Vesta had a magma ocean. So you've got a shorter time for late accretion of material. Core formed quickly. Because it's smaller, it's likely that that magma ocean cooled much more quickly. So it might be different to the Earth. We didn't have a magma ocean that prevailed for a reasonably long time. The other reason that we looked at it was because it's a smaller body, so pressures of metal silicate equilibration, they'll be much closer to those low pressure equilibration. So if you're ever going to see evidence for core formation that mimics the patterns of those low pressure metal silicate experiments, then you'd expect to see it on something like Vesta. So that was our reasons for having a look. Okay, so this is the data for different types of meteorites. Eucrites and diogenites are both thought to come from Vesta. Eucrites are kind of basaltic composition. Diogenites look more like cumulates. There's also a whole bunch of anomalous eucrites. So these are things that were identified as eucrites once, but they've got oxygen isotope compositions which suggest that they didn't come from the same parent body. So they've come from some other parent body. And we looked at angrites as well, which is another parent body. But we don't know where that came from. We also looked at rocks from Mars, and we looked at a few from the Moon. But that was really to, other people had already measured the highly hydrophile elements in those bodies, so it was really to confirm that our data was consistent with theirs. So the data here, they're all for volcanics of one type or another. So what we want to do is somehow get back to what the mantle looks like. Because platinum group elements, although they're highly hydrophile, but they also have variable compatibilities. So they'll be fractionated by partial melting itself. So there's a couple of ways that people have used to estimate highly hydrophile element abundances of the mantle compared to magmatic rocks. Now, on Earth, there's a really nice correlation between highly hydrophile element, pick any one that shows the same covariation, and magnesium, and that's these kind of blue circles. So if you measure a magmatic rock and it's got a magnesium abundance down here, you can work out what the mantle might have if you take appropriate magnesium contents for the mantle. The problem with some of these other planets and planetesimals is we don't know what the mineralogy of the mantle is. We don't always know what the mineralogy of the magmatic of the rocks themselves was that might have affected the composition through fractional crystallization. And for the Moon and Vesta, they're also very reduced. So metal is present as an equilibrium phase on both of these bodies. Vesta can have kind of a third of a percent of the sample can be free metal. And often it's much more than that, but that's because of late chondritic addition. So the problems with using this correlation for places like Vesta is that, well, you can see here, Vesta are the samples in yellow. You can see that samples with very different magnesium contents have a similar range of iridium concentration or osmium concentration, or pick any highly hydrophile element you like. So the approach we took was to use the relative compatibility, incompatibility of the platinum group elements themselves. So kind of give a more internally consistent way of estimating the concentrations in the source of that material. So here I've shown platinum and osmium as an example. Platinum's relatively incompatible, osmium's compatible. So when you make a magmatic rock, that magmatic rock will become enriched in the incompatible element in platinum, and you get fractionation of the platinum-osmium ratio. So then, with the trends that you can see here, you can project back to a so-called chondritic platinum-osmium composition and see what the concentration is. And there are problems with that approach as well, which I've actually forgotten, but someone in the audience might remind me.
Do you have to think about sulfide on this?
Sorry?
Do you have to consider how much sulfide you have in there?
No, I mean this is kind of irrespective of what the mineralogy is. You get fractionation during melting.
Yeah,
so it's kind of independent of the mineralogy.
Yeah, if you have a
correlation. I think the real problem is you're assuming that it started off with a chondritic platinum-osmium ratio. That's the real problem. Different osmium concentrations, but you can do the same. You can repeat this for all those platinum group elements. And that's what we've done here. So this is the mean of those measured. So this is the magmatic rocks, and this is our mantle composition, if you like, our source composition. So what you can see from this data is that, first of all, the patterns of all of those, on all of those bodies, it's chondritic. We've got a flat, highly hydrophile element pattern, so it looks chondritic. So for all of them, the implication there is that these samples have all received a late veneer, that the late veneer was a widespread phenomenon, at least for the terrestrial planets. But the other thing you can see is that for Vesta and the Moon, I mean the Moon's a special case because it wasn't necessarily, it was formed sometime after the start of the solar system. But for Vesta, the abundances of those highly hydrophile elements is a lot lower, 2 orders of magnitude lower than the Earth, Mars and Moon. And Earth, Mars and angarite parent body. So that, at first sight, that's suggesting, well, that's telling us that no, we're not seeing any pattern that would expect from metal silicate equilibration at low pressures. So the easiest interpretation is that it's the late veneer, but that Vesta and the Moon received significantly less of that late veneer material. So our suggestion, kind of the reason that we started the study, was that it might be simply linked to parent body size. So what we've got here is parent body mass against the total highly hydrophile element concentration. You can see there's a reasonably good correlation. The Moon lies a bit off of that correlation, but you have to remember the Moon was maybe formed, 100 million years after. Maybe some people think longer, some people think shorter. And that in this case, then maybe what we're looking at is we just had less time to add this late veneer. It's linked to the parent body. Vesta had a magma ocean that was only extant for, I don't know, a few million years, whereas the Earth was able to receive a lot more of that late veneer. There's also a covariation between the amount of total highly hydrophile element abundance and the oxidation state. So another possibility is that it's not to do with body size, it's to do with redox conditions, and that if you added chondritic material to Vesta or the Moon, it might have still had a magma ocean, but that material, that mantle that it was added to was sufficiently reduced that metal was present as a free phase, and then that metal was able to migrate straight to the core. So it's kind of a different process that's implicated in both of these. So for Vesta and the Moon, you add chondritic material, any metal that's there is present as free metal, can be taken straight to the core, whereas Mars and the Earth and the angarite parent body, a lot more oxidized. You add chondritic material, it's sufficiently oxidized that the iron isn't present as free metal, it gets incorporated into the silicates.
Why do you use IW+3 for the Earth?
No idea. Is that not the...
No?
Probably because Bernie's told me to.
But that's the surface value.
Okay, yeah, so that wouldn't be the deep part of the mantle. That's probably present day, isn't it, that is used? Yeah.
Because otherwise for the deep mantle it's
For the deep mantle it would be 2 or 3.
-2.
Yeah.
Okay, so it's surface.
Okay, so in that case, if the Earth was still reduced then that correlation doesn't exist.
I don't know, it depends
Yeah.
if you take all surfaces or...
Yeah. Well, we don't know when the Earth, kind of the shallow part of the mantle, we don't really know when it was oxidized. Although maybe some people have a better idea than I do. Okay, so just to summarize, late accretion appears to be a widespread phenomenon on the terrestrial planets and planetesimals, but differences in the HSE abundance might be due to body size, so you have more time or more or less time for addition of material, or it might be due to oxidation state. So that's a difficult thing to estimate, as we've just kind of discussed for some of these early bodies. But I'm not sure you can still rule out inefficient core formation. Okay, is there any other way of looking at late addition, at the late veneer? And the answer is yes. And we can do that with tungsten isotopes. Now, tungsten's, it's only a moderately hydrophile element, but you can imagine that if you add a late veneer with a chondritic composition to a mantle with a relatively radiogenic tungsten isotope composition, that you might see just a small shift in that tungsten isotope composition. And one of the nice things about tungsten isotopes is we can measure them very precisely. We can measure them down to kind of plus or minus 5 parts per million. So we can make, nowadays, we can make very precise measurements of tungsten isotopes. So the place where people first looked was some of these very old terrains on Earth. And in particular, the first place that people looked was Isua. Isua is in West Greenland. It's volcanics, sediments. They've all been subject to metamorphism and deformation. And those metamorphosed rocks, they give an age, kind of a minimum age of about 3.9 billion years. These are some images from Isua. And you can see they kind of look like rocks of the present day. So these are deformed pillow basalts. And these are conglomerates with rounded granitic pebbles in. So both of those are kind of clearly indicating there was water at the Earth's surface like 3.9 billion years ago. Which is, I guess we all knew that anyway. But it's nice to see in a rock rather than in a zircon or something. So this is data, this is tungsten isotope data that Matthias Wilbold published a few years ago. And he measured tungsten isotopes in some of these rocks from Isua to very high precision. And he found that they are slightly more radiogenic than present-day volcanics. And they're more radiogenic by somewhere between 15 and 20 parts per million. So it's a very small difference, but it can be resolved. That measurement can be resolved. And his interpretation of that data was that the mantle that melted to make these rocks, to ultimately make these sediments, it hadn't received its full complement of the late veneer. So the late veneer hadn't been mixed into that mantle source. Either it hadn't been added or it hadn't been mixed in. And shown on this figure here is just showing some, so that's the measurements that he got from Isua, that's the present day mantle, and these are the mixing lines that you might expect if you added some chondritic late veneer. And these are different types of chondrite. They're both ordinary chondrites, I think. So then in 2015, there were a couple of studies, Thomas Kruger and Mathieu Tugour. They both published more, I think it was it's the same volume of Nature. And what they did, they went back to the moon and they measured much more precisely the tungsten isotope composition of lunar rocks. And they found that, as opposed to before, where the lunar composition was kind of indistinguishable from the terrestrial composition, they found that it was 25 to 30 ppm more radiogenic. And so the model that's kind of shown in the figures from both of their data sets is that, if you'll remember, that the moon received 2 orders of magnitude less late veneer. And so the interpretation then is that the moon has received very little late veneer, but enough to give it a chondritic pattern, and that the difference between the lunar mantle and the present-day silicate mantle on Earth is due to that difference in the amount of late addition of material. So more or less the same result that they got. So then what I did, or what we did, no, what Chris Dale did, in fact, it wasn't me, what Chris Dale did was to go back to these Isua samples and measure highly hydrophile elements at the same time. Now I should add that at the same time, Hanneke Rizzo did exactly the same thing. She went and measured some, so Hanneke was a PhD student here, I think, yeah. And she was in Montreal, I think she's now in Vancouver. She's going to Vancouver. Yeah. Well, she's in Montreal at the moment. So she did a study at the same time, and her work was published just before ours. Well, it was published a year before ours. But I'll show you our results and compare those to Hanneke's as well. So we measured highly hydrophile elements in a bunch of these different rocks. Some of them pilobasalts, some of them ultramafic amphibolites, some of them kind of orthogneisses, more evolved kind of rock types. Those are the patterns we got. So you can correct, because these are terrestrial rocks, you can use this covariation to correct, more or less, and you you get abundances in the mantle that are somewhat less than the bulk silicate earth using our samples. If you take this compatible-incompatible approach, then again you get something like kind of 3 nanograms per gram of osmium in the source compared to 3.5, I think, for bulk silicate earth. So what these data suggest is that the highly hydrophile element abundances are lower. They're not the full complement. At the same time, with Thomas, we remeasured the tungsten isotopes. This is the data of Haneke's, which shows exactly the same thing. So they all show this slightly more radiogenic composition in tungsten isotopes compared to the present day, compared to most present day volcanic rocks. So then, if you take our tungsten isotope data for Ishua and our mass fraction of the late veneer calculated from the total HSE abundance, then it very nicely falls on that mixing line for late addition. So the implication then is that this terrain, the mantle that this terrain that melted to make these rocks in this terrain, it hadn't received its full complement of the late veneer. Now that kind of looks nice. It all fits really nicely. But then I think Haneke found her point lies over here. So full complement of highly hydrophile elements, same tungsten isotope anomaly. So that shows there's a bit of a problem with measuring highly hydrophile elements in these ancient rocks that have experienced metamorphism. I don't think there's a problem with either technique, either approach or either technique. But then it gets worse, because about the same time, people measured tungsten and highly hydrophile elements from a whole bunch of terrains, of these early Archean terrains. And you can see they're kind of all over the place. It's not a simple mixing between the moon and the present day bulk silicate earth. Now maybe some of that reflects some initial degree of heterogeneity in the tungsten isotope composition of the earth. Maybe. Maybe some of that reflects mobility of tungsten. It's a relatively mobile element. But at some point, at least when this figure was made, it was thought that at some point you're mixing all of these terrains and you're getting something like the present day bulk silicate earth. So just before I move on, just again, I'm not convinced that this is compelling evidence for the addition of a late veneer. Highly hydrophile elements, maybe, but I don't see a simple mixing between. Well, you can say that there's a broad mixing between the moon and the earth, but some of these are quite variable. So the question is, when do these different bits of the mantle? Yeah.
So when you say this highly hydrophile element content, you're
Yeah.
implying the mantle budget, right?
Yes.
But you are coming from those rock sample.
Yeah, we're coming from, and that's always the problem.
Yeah.
How do you get from a crustal rock
Yeah.
that is the product of melting, and some of those hydrophile elements are incompatible, some of them are compatible, and get back to the mantle? So I guess what I would say is that for the Komatiites, they're probably a lot more robust. They have a much higher platinum group element concentration because they result from higher degrees of melting. So you tend to exhaust the platinum group elements in the mantle source. So if anything is reliable, it's these diamonds in terms of the highly hydrophile elements. But they still show you this heterogeneity.
How about the late metamorphism or hydrothermal alteration?
So for the highly hydrophile elements, they are relatively immobile. For tungsten, it's relatively mobile. So there is a possibility with some of these terrains that tungsten has been mobile. Some people don't like that, but it remains a possibility because it is a relatively mobile element. Okay, so somehow we think that we've mixed all these, we've got these heterogeneous parts of the Earth, of the early Earth, and they've all been mixed back in together, but they haven't. And this is data that was published just last year by Haneke, again, and she looked at tungsten isotopes in in basalts from Baffin Island. So Baffin Island is part of the Iceland-Greenland plume, and it's kind of a manifestation of the earliest parts of that plume, so it erupted about 65 million years ago. And this is her data, shown here. These green triangles are off of Baffin Island, and you can see that, in particular for one of these samples, it's more radiogenic than the present-day mantle by about 50 parts per million, which is much higher than we see in any of those early terrains. So the incredible thing that we're seeing there is that these heterogeneities that must have been developed in the first 50 million years of the solar system, I'm kind of saying nice things about someone else's work, which is, I'm not sure that's what I was invited here to do, but it seems appropriate as Hanneke was studied in Claremont. So what this shows is that these things have been preserved in the mantle over much of the age of the Earth. So late veneer on Earth, Earth's earliest mantle, it does preserve these differences in tungsten. Some of them are consistent with the addition of a late veneer, particularly when you compare it to the lunar composition, but it's not systematic. So the early mantle appears to be highly heterogeneous, as is the modern mantle. How am I doing for time?
1 minute.
1 minute. Okay.
For break.
Okay.
We can stop here for coffee if you want.
Yeah. No, it's either that or I show neodymium stabilized tape data for sulfides.
So we can have a break for.
So maybe the late veneer hit the earth during the mantle weather in
Coffee break.
like if it's all homogeneous and
Yeah.
you have a bit mixed in there.
Let's
To
do the
come
final
back to the first question, like say, oh, we need this increasing of the
Yeah. So that is an idea, and there is a model for that. In the sense that if it's less that maybe it was already solidified, but it's that the external part of the Earth received a disproportionate amount of that late veneer, and there's evidence from komatiites. If you look at the komatiite data, it's another thing, I couldn't show that as well, but there's evidence from komatiite data that the komatiites, they progressively sample highly hydrophile element concentrations over kind of period from about 3.5 to 2.7. You see the systematic increase in the highly hydrophile elements that they sample. And that's been taken by some, or it's been interpreted by some to indicate that there's been a kind of slower mixing in of the late veneer as that's been mixed into the mantle. But whatever mixing has occurred, it hasn't been entirely efficient at mixing in the tungsten.
It can be heterogeneities in the iron content that is retained, isn't it? If you change, for example, the upper mantle that was largely molten could have lost the iron,
Yeah.
and the lower mantle could have retained more.
Yeah.
That makes a huge heterogeneity in
Yeah,
the,
and I think that's one of the models, at least, has been, at least for some of those early terrains, has been that localized metal-silicate equilibration has played a role in generating a heterogeneity.
Yeah, but then you're remixing some things, and then you can recreate some crust or some basalt or whatever from the mixing of different parts of the mantle, which initially contain more or less irons, which change completely the picture.
Yeah. For Baffin Island, there's a whole host of other traces that suggest that the source of those basalts is extremely primitive. We've got high 3,4 helium. The lead is very unradiogenic, it sits on the geochrom. There's all sorts of evidence to suggest that it's very primitive material that hasn't been mixed back into the mantle.
You said that tungsten could be mobile.
Yes.
Okay.
Well, I think it is mobile.
It is mobile,
Yes,
but,
yeah.
but to which extent? Did people maybe try to measure tungsten isotopes in similar type of rocks? One metamorphose, the other one unmetamorphosed?
No one's done anything clever like that. I mean,
Because on people like to
or
granulite facies,
or careful
it's
like that.
quite a
Yeah.
high.
So that's really what people should do now, is they should look at the extent to which, because
can
it's
be
rather remarkable that all of these rock types have the same initial, for example. Some of these are highly evolved, but then you could say, well, they're all coming ultimately from the same source, so they've just inherited that tungsten anomaly. But it's known to be mobile, fluid mobile. And in a terrain that's experienced kind of amphibole-like
Amphibolic
fascism.
to granulite
minimal,
features.
yeah.
Yeah.
Take it, right?
Mhm.
I'll have to take more questions.
On va avoir une pause café d'1 quart d'heure et on revient après.